Hello, and welcome to today's webinar on avoiding downtime disasters. My name is Dan Maskell, and I'm Product Marketing Manager for Vigilent, and I'll be hosting two guests today. The first is Dr. Nicole Perlmutter. She's the Director of Environmental Sustainability at Akamai Technologies. Nicole oversees the strategy and execution of environmental initiatives across the company and spends a lot of time collaborating with network engineers, innovating around the energy efficiency and productivity of Akamai's global intelligent cloud platform. Nicole has over 14 years of experience in high-tech communications, including sales, marketing, product design, development, and management. Our second speaker will be Dennis Szymanski, Senior Project Manager in the Energy Efficiency and Power Quality Division of EPRI, which stands for Electric Power Research Institute. Dennis is an expert in data center technology and is currently investigating ways to make data centers more energy efficient and reliable. Dennis was recently quoted in the New York Times article on data center energy efficiency. So the layout of this webinar is going to be about 45 minutes of discussion from myself, Nicole, and Dennis. And then we'll use the last 15 minutes for questions from the attendees. If you have questions during the webinar, please enter them in the chat panel of the QA section in WebEx. And then at the end of the webinar, I will read them and direct the questions to the appropriate panel member. So Dennis, Nicole, and I will be discussing the operational challenges that data centers face for ensuring uptime in their facilities around the clock. As data centers are becoming larger in their sheer size, the IT equipment and environment is becoming more dynamic, and as the equipment in those facilities on the IT side and the cooling side are becoming more sophisticated, it's becoming more and more difficult to avoid downtime incidents. And downtime costs about $5,600 per minute, and actually in financial institutions, that number is closer to $5,600 per second. And about one-third of downtime events are cooling related, and that's going to be the focus of our discussion today. Now, when you start to look at risk in a data center, there's a certain metric that we all kind of use to evaluate that risk, and that's redundancy. And from a cooling perspective, the way that redundancy or cooling redundancy is measured is based on the amount of cooling capacity that's installed in a facility. And typically we find that there's twice as much cooling capacity than the actual IT load. So there's twice as much redundancy in a facility. But as the business grows and as the IT load grows, that redundancy margin shrinks, and people perceive that as a reduced or increase of risk in a data center. And so the industry solution for mitigating this risk is two things. The first is to install more cooling capacity, to increase that headroom. And the second is to turn that cooling capacity on and leave it on all the time. And so this idea of redundancy is actually more specific installed redundancy. And I'm going to make the point that installed redundancy is actually misguided. And not only is it misguided, but it can actually increase the risk of a downtime event. What is critical is operational redundancy, and there's a difference between installed redundancy and operational redundancy, which is important to understand. Here are some case studies from some sophisticated IT and data center owner-operators that have had operational outages recently. And the one that I'm going to mention quickly is the Facebook data center up in Prineville, Oregon, where a BMS glitch had caused the outside air dampers to close, which caused condensation to build up in the IT equipment and causing some of that equipment to fail. Now, Facebook, being a pretty sophisticated data center owner-operator, and they probably had a pretty sophisticated cooling system with enough capacity, encountered a operational issue or an operational redundancy issue that caused an outage in that facility. And so what's the difference between operational redundancy and installed redundancy? Well, if we look at a typical data center with a crack unit on a raised floor environment, and you have a cold aisle with 2 rows of IT equipment, you've got crack unit taking hot air on the top and discharging cold air out the bottom. And so you develop a cold underfloor plenum, and then the hot air, as it rises up into the ceiling, develops a hot, warm thermal plenum above the IT equipment. And so what you'd expect is that as the cold air is discharged up through the perforated tiles into the cold aisle, it is then sucked through the IT equipment, the air is heated up, and then raised up into the ceiling, into the thermal plenum above the IT equipment. But what actually happens when you have an excess amount of cooling capacity is you have an excessive amount of airflow. And so the airflow is actually bypassing the IT equipment and raising up to the ceiling and mixing with that hot thermal plenum. And what happens is when you have cold air mixing with the hot thermal plenum is that hot air in the ceiling is actually displaced down into the environment where the IT equipment is. And it's displaced over the top of the racks, around the side of the racks, and even through the racks or under the racks, which causes or results in mixing. And that's what causes hotspots. It's an excessive amount of airflow that results in mixing, which causes hotspots. And so what is the solution when a facility operator has hotspots? Well, they say, well, I'm not redundant enough. I need more cooling capacity. And so the solution is to install more cooling capacity. And of course, if you install more cooling capacity, you're just increasing the airflow in the facility, and an excess amount of airflow in the facility causes more mixing, which leads to more hotspots. So in fact, when you think you're increasing the redundancy or installed redundancy of your facility, you're actually making the situation worse. And so how do we look at this and attack this from an operational perspective? Well, the first thing is you need to get data and measure the environment. And these green dots here indicate temperature sensors, measuring granular temperature data at the rack level. And you probably want to poll on a sub-minute frequency rate. And so you want to obtain information about the temperature in the thermal environment. And the next thing you want to do is obtain information about the cooling units themselves. So this shows a temperature sensor on the return air temperature and the discharge air temperature of every cooling unit. Now, once you have information about the thermal environment and also the cooling performance, then you can start to intelligently control the cooling to mitigate those hotspots and manage airflow in your facility. And it is through this aspect or through this vehicle that operational redundancy is achieved. Now, you could go out and buy a Volvo, which is the safest car on the road, and drive down the highway at 80 miles per hour. But if you're blindfolded, you're not going to be operating that vehicle very safely. And it's the same kind of analogy here. It doesn't matter how much you have installed or what kind of equipment you have installed, but it's how you're operating that equipment that is important. Now, the last example was I discussed just a simple one-crack model. But of course, in the practical world, a data center room has many crack units. 20, 30, 40, or even up to 100 cooling units in the same space. And this image that you're looking at here is an influence map from a Vigilent system. And it's showing the relationship between cooling units and how that affects temperatures on the data center. And so this unit, crack 2-2 in the lower right-hand side, when that unit is operating, it is influencing the temperatures as shown in the color gradient. So all the areas in blue is where it actually gets colder, but the areas in red is where it actually gets hotter. And this is surprising to people. It kind of goes back to the idea of if I install more cooling equipment, then I'm going to have more cooling redundancy in my data center, but that's not correct, and that's what this map is showing. So when this unit is turned on, it actually gets hotter in those specific locations. And why does it get hotter? Well, from what I just described, the excessive amount of cooling and airflow causes mixing, which causes the localized hotspots. So what does a operational redundancy system look like? Well, this is an example over the course of a day of a downtime incident where a chiller had failed in a data center. And a cooling control system was installed in this facility, and it had responded appropriately. So what you're looking at here is on the x-axis is a 1 day from midnight to midnight. And then on the y-axis, on the left y-axis, is the average fan speed, which is indicated by the blue line. This was a CRAW deployment where the Vigilent system was controlling VFDs. And then on the right y-axis is the average temperatures, indicated by the red line. So what happened at about 2 o'clock in the morning is the chillers had failed, and none of the facility staff were there at the time. And you can see as the temperatures start to go up, the fan speeds immediately respond to that and start ramping their fan speeds up to provide as much cooling as possible within the using the chilled water loop. Then at about 4 o'clock in the morning, the chillers restored just briefly for a few hours, but then failed, and you can see the temperatures go up to about 86, 87 degrees. And again, the cooling system responded and provided full cooling until noon, when the facility staff had come in the building, and it took them a few hours to restore the chiller. Once temperatures had then dropped back into adequate levels, the Vigilent system dropped fan speeds along with it. And so by the end of the day, the temperatures and fan speeds were back to where they were when before this incident had occurred. And so how do you know as a facility operator if you have downtime risk in your facility? And it really starts with data. If you're driving blind, you just have no clue as to how your facility is actually operating. So that's data on the cooling, the thermal side, so granular amount of data where the rack inlet temperatures are, but then also about the cooling units themselves to understand their performance and efficiency. And this data can begin to give you visibility into the operational redundancy and operational dynamics of your facility. And again, the installed redundancy is misleading. It's not what you have installed or how much you have installed, but it's how you're operating that equipment. That is important. And what kind of this drives a very proactive behavior, because you can use this data to start predict when things might fail before they actually do. In a lot of cases, the data centers don't have this data, and so what they do is they have a very reactive approach to how they operate their facility. They wait for something to fail, and then they run around as quickly as possible to fix it before a major event occurs. But with the data and with an active cooling control solution, you can be more proactive in avoiding downtime events. So now I'm going to pass the presentation off to Nicole, who's going to talk about her case studies and her findings in a little bit more detail. So Nicole, you are unmuted, and you may begin.
Great, thanks, Dan. So as Dan mentioned, I'm Nicole Thiel-Molter from Akamai Technologies, and I'm the Director of Environmental Sustainability, but a lot of the work I do is in energy management of our network. As I'll explain later, it's a very large portion of our energy consumption of our company's operations. So for those of you who are not familiar with Akamai, we have a global network, content delivery network and service. We support the world's largest web properties in many, many different markets, including media and entertainment, high tech, commerce, public sector, financial services, and automotive and manufacturing, all of whom having their websites up and running is very, very important. And we sit between our customers and users and our customers' data center infrastructure, providing high performance, high availability, high security of their website content to their end users. So we do this, we deliver this service on our globally distributed cloud platform, which consists of over 120 servers currently and growing that are reside in 80 countries in well over 1,000 data centers worldwide. So we have quite a distributed data center architecture. The key thing here, though, is that Akamai, while we own and operate our servers and we manage those very, very tightly, we colo our equipment in third-party data centers. So we have no operational control over those data centers, but it's still very, very important for us that those data centers remain up. And of course, we contract with these third-party data centers. And what's important to us, not only from an operational perspective, but obviously from a cost perspective, it's important that they not only provide 100% uptime, but also that they provide their services at low cost and high efficiency. I think everybody really understands that a data center operator's ultimate goal is 100% uptime of the IT equipment. So however you get there, so long as the IT equipment is up and running, everyone's happy. However, subsequent to that goal, that also means keeping the IT equipment consistently cool, because if you don't, you're going to have operational problems. But you don't want to, not only do you want to keep it consistently cool, but you don't want to overcool because that's inefficient. In addition to that, you also want to be able to identify potential issues early on when possible. And then, of course, you also want to control your energy costs. So how do we do that? So the risk of for uptime can be in the form of overheating of IT equipment. And so IT watchdogs concluded that an increase from 68 degrees to 86 degrees can reduce the long-term reliability of IT equipment by as much as 50%. And when cooling fails, temperature can skyrocket in a matter of minutes, as we saw in one of Dan's graphs. Now, it's not really the problem of high temperature per se, because ASHRAE has come out with new standards for IT equipment saying that they can handle 80 degrees plus in the equipment. It's actually the consistency of the cooling. So it's a matter of vacillating temperatures significantly is what does the damage to the equipment, not necessarily the high temperatures per se. And we'll talk a little bit more about that later. Some key sources of overheating generally are lack of airflow management, lack of visibility into where the heating problems are happening, and then also lack of ongoing feedback control to manage the cooling around the data center. And your DCIM can provide you solutions to all of those. So what do we mean by airflow management? So this graphic just beautifully lays out a perfect airflow where you have cool air coming into the cold aisle section and going into the front end of your servers, assuming that they're oriented correctly, cooling the servers, and then the hot air is being immediately sucked out into the return air plenum such that the servers only see cold air, and the hot air is not mixing with the cold air, which obviously is inefficient and provides higher cooling temperatures to your servers, which is also very inefficient. This is another graphic of it's a heat map showing what happens when you have cool air short-circuiting. So in this case, you can see this is probably either a missing blanking panel where you have a gap in the rack where you don't have a piece of equipment, so you're short-circuiting the hot air into the cold air aisle, or it could just be that someone had put a toaster in this space and you're seeing the heating going into the cold aisle section. But either way, it's very inefficient and it's not helping to cool your servers. But it's good to have that visibility to see that that's happening because maybe nobody notices it otherwise. This heat map is a great way to provide visibility into what no airflow management looks like. So in this case, for example, if you're a data center operator and you're standing in the lower right-hand corner of the room, you think everything is going fine and dandy. Or you may think that maybe it's a little chilly, but at least your servers are being cooled, where in fact the left-hand side of the room is being overheated and certainly hot spots. And you might be able to discern that by walking around and you're maybe going from an area of cool to hot, but in general, you're not really going to get a good idea of how efficient or inefficiently your room is being cooled. And so it's a big problem. If you have airflow management, you might be able to minimize this situation, but again, you don't necessarily have visibility into whether your airflow management is working or not. And as a result, you get stressed out operators because they don't know from moment to moment whether or not their IT equipment is being properly cooled or whether they have an overheating situation, which will then result in some kind of operational failure. And we want to try to avoid that. Some best practices of airflow management are simply things like blanking panels. So this photo on the left shows a rack of servers that is missing servers in the top rack, and so there's a huge gaping hole, which of course cool air is going to flow into the hot air, or hot air is going to flow into the cool air, and you have mixing, inefficient heating, and certainly inefficient from an energy perspective. The answer really is to simply plug those gaps with blanking panels, and you may have to put tape around where you have cabling and that sort of thing, but generally it's a very simple, low-tech, low-cost solution to improving the operational efficiency of the cooling in your data center. And a second best practice, again, relatively low cost and low tech, is hot aisle or cold aisle containment. The photo on the left shows your meat locker type containment, where you have curtains that are separating the cold air from the hot air and allowing, in this case, it's a cold aisle containment because you can see the perforated floor tiles blowing the cold air into the cold air aisle, and the curtains are keeping the cold air and the hot air from mixing. On the right-hand side is a little more sophisticated implementation of your containment where you're using more plexiglass, and you have, in this case, some solid doors, sliding doors at the ends of your aisles to prevent the mixing. So going back to the idyllic picture of what you're trying to achieve with this airflow management is simply that your airflow from the cold aisle goes into your servers, comes out the back end hot, goes directly into the return air for your crack unit. Now, an important thing to understand about this perfect airflow is that when you're maximizing the delta between the crack unit supply air, the cold air, and the hotter return air, you're actually maximizing the efficiency of the crack unit. So you're not only improving the cooling of your servers, but you're also improving the efficiency of your crack unit, the cooling efficiency and the energy efficiency of your crack unit. And furthermore, you're generally able to raise the supplier temperature of your crack unit and still have the exact same cooling efficiency that you have at a lower temperature where you don't have the good airflow management. It's counterintuitive, but what's nice about that is you're achieving the same ends with much, much less energy. And in addition, it also enables you to, if you want to play with higher set point temperatures, you can do that as well. So that's kind of a segue into my just an aside here, which is best practices in airflow management from an operational perspective will also get you significant data center energy efficiency gains. And you might be able to see your PUE, your data center efficiency drop from a 2 down to, say, a 1.4, so that you can get 30 to 60% reduction or improvement in your energy efficiency. And that's through airflow management, but it's also to maximize your energy efficiency and also your operational benefits, is you need that ongoing visibility and that ongoing feedback control. Otherwise, you may have an optimal conditions in the beginning, but as over time, as things change, as equipment comes in and out, as floor tiles get moved around, you're going to lose that optimization. So you really need that ongoing visibility and feedback control that the DCIM gives you. So some of the ways to maximize data center efficiency through the exact same airflow management implementations is you're going to eliminate overcooling. So as we saw in that one heat map where you're overcooling one side of the room and you're undercooling other sides of the room, your ongoing management dynamic control is going to keep that even temperature set point. So you're minimizing your efficiency or your energy usage while providing optimal cooling. As I mentioned before, you can also play with higher set point temperatures. The ASHRAE standards now say that we can get into the 80, 85, even 90 degree set point temperatures for equipment. The important thing, though, is to make sure you're at a consistent temperature. So it's the vacillation of those temperatures that really cause harm and risk to the equipment. And finally, you can implement air side and water side economization of your cooling system, because now you have tight control over the temperatures in the data center to ensure that you don't have any risk to your equipment through economization. Here's an example of a case study where they raise the set point temperature to 77 degrees, which clearly you can save a significant amount of energy in doing that without risk to the equipment, though. But the key difference here in this case study is look at what happens when you don't have any feedback control and visibility into your temperatures. In this case, they raise the inlet temperature to 77 degrees, and then the comparison is with dynamic control. So in the baseline situation where you have no dynamic control, no visibility, you can see a significant number of the racks are above the targeted inlet temperature of 77 degrees for a significant period of time. And that's going to introduce a lot of risk to your equipment because you're not controlling that high endpoint temperature. But with the dynamic control, you can sit at a steady 77 degrees with little risk to your equipment. And as you can see, a very few number of racks were above that 77 degrees, but for a very, very small percentage of time. So it's a very tightly controlled environment that reduces your risk, even at that higher inlet temperature. So significantly saving a lot of energy and energy cost savings there. So ultimately, you can't manage what you can't see. So hopefully I've impressed upon you that it's like a doctor trying to diagnose a patient. They can glean a lot from, looking down your throat or taking your pulse or your blood pressure, or not even your blood pressure, because they can't do that without a special piece of equipment. But if they really want to finely tune and diagnose and make sure they're solving an immediate problem, but also potentially a long-term problem, it's having those blood tests, having the blood pressure, having a lot more detailed visibility into your patients that's going to enable you to make sure that you have the ability to currently diagnose the current situation and also foresee any potential future issues. So let's go back to that heat map where we had the overcooling in the lower right and then the hot spots and the overheating on the left-hand side of the data center room. So Akamai implemented the Vigilent DCIM system in our Bent Street data center, which is a corporate data center with corporate equipment. We own and operate we lease the facility, but we own and operate we operate the data center equipment. And so we've been running this for many, many years, this data center. And in 2011, we implemented the Vigilent system. And the first thing we saw was that one of our crack units, the supplier was actually hotter than the return air. So you can imagine that when we discovered that, we were just scratching our heads thinking, you know, what a waste that was to have that crack unit running for so long. And you can see on January 10th is when we turned on the Vigilent system, and immediately the supply air temperature dropped well below the return air temperature. And going back to my comment earlier about maximizing the delta between the supply air temperature and the return air temperature maximizes the cooling efficiency of the crack unit and also the energy efficiency of the crack unit. So you can see that it had immediate benefits, and it was certainly a surprise to us about how poorly that one crack unit was doing and potentially doing damage to the whole operation. So some other things that we saw, the crack unit, one of the crack units was blowing warm air into the ducts, as I mentioned, but we also found inefficient air duct flow that caused reverse airflow in some cases, which again led to inefficient cooling. And we also noticed frequent on-off cycling of the compressors of the crack units caused temperature oscillations, which again is not what the equipment wants to see. It wants to see consistent temperatures, not oscillations in temperature. With dynamic control, we were able to permanently turn off one of the 5 cracks, the one that was actually heating, not cooling. We saw much more uniform rack temperatures, and we are now able to turn off 2 of the remaining 4 cracks during the wintertime when it's much cooler outside. So you can imagine the amount of energy and money that we saved in those situations. And furthermore, we freed up cooling capacity for additional IT. So previously, we now have another crack unit that we could turn on if we wanted to, making sure it's now cooling rather than heating, if we wanted to take on more IT equipment. And for someone who's in the business of colo, that could mean you're taking on more colo clients, which is more revenue for you if you're effectively increasing your cooling capacity by optimizing the cooling equipment and operations. So here's just a quick graph of what we saw in terms of the money spent and the energy used in our Bent Street data center. So we have a historical trending of those, and then we did do some efficiency measures such as airflow management, and you can see a slight decrease in the energy usage and monthly expenditures on energy. However, it wasn't really optimal because we didn't know that we could reduce, say, the fan speed of the crack units or raise the set point temperature, do any of those other, that's where you really gain the energy savings and the cost savings. But when we implemented the Vigilent system in January of 2011, you can see there was a significant drop in both the cost savings or the energy expenditures and then the energy usage as a result of being able to optimize the crack units, the operations of the crack units and raising set point temperatures. So as a result, you have much more relaxed and confident operators because they feel that the data center equipment is being cooled to the optimal level with and making sure they're going to get notified if a problem arises or if there's trending that indicates that a problem is on its way. Much better scenario. So since Akamai is actually 100% coloed of its network equipment, we wanted to take a look at what are our colos doing as far as temperature management, operational management, and efficiency management. And we realized, what we found was the vast majority of our colo partners weren't implementing DCIM for reliability and efficiency, and we wanted to really understand why. So the first thing we understood was that energy costs are passed through the colo clients, and therefore the colo data center doesn't necessarily have a direct financial incentive to improve energy efficiency because ultimately the client pays for that inefficiency. And then, of course, no one tends to get fired for being energy efficient, and generally they don't get promoted for being efficient. They only get pat on the back for uptime and or they get regaled for if there's any kind of problem, operational problem. So as Dan said, they play it safe. And colo clients, and even colo clients, aren't incented to push for energy efficiency because generally the way they pay for colo space, there's not a direct impact on efficiency because you generally pay for the amount of power that you're supplied to the rack. Ultimately, the lack of data that that you can use to demonstrate improved operational conditions. So there's no data to show your boss. This will help us improve our the operational conditions within the data center and the IT equipment, and also meet our SLAs, because right now, for most SLAs, it's the crack supply temperature, not the server inlet temperature, that is being monitored. And as a result, you could have overheating all over the data center, but as long as the supply temperature is within the SLA bounds, that's all that you need to meet. In addition to that, there's no data to build a business case for efficiency and operational benefits. So as we demonstrated, if you implement the DCIM and the operational controls, the ongoing operational controls, you can effectively increase your cooling capacity. For a colo, that means being able to take on more colo clients and ultimately more revenue, and also save on the energy on the energy side. So there's a lot of benefits, but what we realize that right now there's a big hurdle, possibly because of educational and also lack of data and visibility. So finally, I just want to impress upon you, I'm not a control freak, but in this case, I do believe there's definitely a need for control. So if you can gain the visibility of what's going on in your data center from a temperature operational perspective, you can see what you need to do for airflow management. Once you implement the airflow management, you can and implement the dynamic cooling controls, you'll see the benefits of those, and then and as things change within the data center, as things get moved around, new equipment's added and taken away, you still have that ongoing visibility, maintain the airflow management and the dynamic cooling. This leads to your ability to build a business case for DCIM. You can attain those ideal operational conditions. You can improve reliability and maximize your cost savings. And then again, ongoingly, as things change in your data center, you can continue to achieve those ideal operational conditions and maximum reliability and maximum cost savings. So thank you very much.
Thank you, Nicole. Up next is Dennis Szymanski. Again, he's a senior project manager for EPRI. And we will unmute you right now, Dennis. So you're up.
Okay, thanks, Dan. I appreciate that. Basically, I think everybody nowadays knows about what the Green Grid did with defining what the power usage effectiveness is for data centers. That's PUE, and it basically takes the total data center power and divide it by the IT power. And the facility end of that has everything from the the power distribution units, the UPS backup generators, the transformers that take the voltage down to the usable voltage for the IT equipment. It also includes the cooling. For large data centers, you've got cooling towers and chillers and everything else. For smaller data centers, you've got computer room air conditioners. And you've also got things like lighting that you should include in the total power. And it's a lot easier to do this with a dedicated data center building, but even within commercial buildings, which is where basically 99% of the data centers are, these small server rooms, you can also utilize this technique to figure out how efficient you are. As I said, the closer you get to 1.0, the better you are. The EPA a while back did a survey of over 100 data centers in the U.S., and they found that there's a wide variety of efficiency of these data centers, everywhere down to 1.25 up to almost 4. With the average being 1.91, which means that for every 100 watts of IT load, you need 91 watts of cooling and support load to support that IT equipment. Many of the data centers don't even know what their PUE is because they don't have the instrumentation and the metering in order to figure out how efficient or inefficient they are. One way to look at all these data centers in the U.S. is the ones that are always in the news are the Apples, the Facebooks, the Google data centers, which are huge data centers. They're totally dedicated just for the computers that are inside there. There's no offices or anything else in there. And they've also got staffs of architects and electrical and mechanical engineers, and they actually build quite efficient data centers. So they're doing a lot of good things, but that's like less than 1% of the data centers in the U.S. The other 99% of the data centers are, all these other loads, everything from banks and hospitals to universities and city halls, which are usually have their data centers within a piece of a commercial building, and they almost constantly struggle with, reliability issues, hotspots, running out of space, running out of power. So they don't have a whole bunch of staff members that are dedicated to working on the data center and making it efficient. So they struggle an awful lot. What DCIM is trying to do is trying to get the power of the people in the process all combined to make the data center as reliable as possible, while working on energy efficiency, thermal management, operational procedures, trying to look at best practices. But what you basically need is you need data that both the IT staff and the facility staff can use together to figure out what's going on, how are you doing, and how to fix the problems that arise, routinely in data centers. So, basically what you need is data. The next slide. From looking at data centers, across the country, and around the world, if you look at the total load, it's amazing how flat the load is. The load does not vary all that much, hour to hour, day to day, month to month. So this is a very typical thing that you see with data centers, because the computers are constantly running, and you constantly have to cool them. So nowadays, how are data centers powered? Some of the bigger data centers are trying to integrate PV panels and fuel cells and windmills, renewable energy into their facilities to do a bunch of things. To be more green, to try to reduce the electrical load for the utility power. So when you install solar panels, it doesn't do you much good at night. Windmills are great when the wind's blowing, but you get nothing when the wind's calm. So you still need the utility power, and even utility power is not what you'd always expect if you look at the Northeast after Superstorm Sandy. Big problems. And what are some of the things that are making data center loads grow? I keep having to update the number that I put down on some of these slides. Like for Facebook, I think they may be up to 1 billion members right now. Doing all sorts of stuff, including, sharing details on what they had for lunch today. You look at the Apple Store with all the apps that they've got there for the iPad and the iPhone. They've got $1 billion, 500,000 square foot data center with room to build another one right next to it. It's to sell apps and to sell the iTunes and stream videos. And what's amazing is that many of those apps need another data center in order to operate. The example I use is if you're in San Francisco, on a business trip, and you want to find the closest Italian restaurant from your iPhone, there's an app for that. So but the thing is, there has to be a data center somewhere that collects all that information, finds out where you are, your GPS location, and locates the 5 closest Italian restaurants that you can then call up a taxi cab, because there's an app for that on your iPhone, and have it dispatched to where you are. But that data center dispatcher needs to have a data center to figure out where his vehicles are and where you are, find the closest one, and dispatch it over to you. So all these things are making data center more data centers and making the size of them grow. Cloud computing, as Nicole said, a lot of the data centers now are colos, where you don't own the data center. you just put your equipment in there, or you actually can rent the equipment in these cloud computing data centers. Email keeps going like gangbusters, and we keep attaching bigger and bigger files to these emails, going back and forth, and photographs and everything else. So the next slide. So there's constantly things that are going on. Now with electronic medical records, people are living longer. There's more procedures being performed, and all that data. I want my data stored forever. Well, maybe not forever, but as long as I'm living, I want all that data available to have the doctors take a peek at it. And you look at even the electric utilities, the smart grid. They're installing tens of millions of these smart meters, and from these smart meters, they used to get one reading per month, for your bill. Now they get readings every 15 minutes, so you get 3,000 readings per month, and you got to store and analyze all that stuff in ever bigger data centers within the utilities too. So and you got things like gaming. The PlayStation has over 77 million users, and just looking at some of this traffic that goes back and forth, France Telecom is complaining and negotiating with Apple and Google because looking at the traffic on their network in France, it's growing 5% every week. So there's just a huge amount of data that's going back and forth that is very important, because everybody wants that data available. Whether you're at work, whether you're surfing the web with your iPhone or your iPad or whatever. What EPRI did over the last year is we took our own data center and we worked with Vigilent to install their intelligent energy management system. The good thing is that we had the data center that we have here in Palo Alto, California, is about 12 years old, and it's got a pretty good hot aisle cold aisle arrangement. There's no containment anywhere. There's two 30-ton direct expansion crack units, and what we did was we put each of those 30-ton crack units have a 10 horsepower fan, a motor to drive the fan that was also like about 12 years old. It's not rated for being run by a variable speed drive, but it works just fine. There was a lot of concern that the motor wasn't rated for that. If you take these DX units and you slow down the airflow, there's concern that you're going to have all sorts of condensation and freezing problems. When we install these variable speed drives on the fan motors, we slowly decreased the speed of the fans and took a look at what the energy savings was. Okay, the decrease in fan power when you decrease the fan speed. It's actually the cube of the fan speed. So if you reduce the speed by half, you're actually saving a huge amount of power. And we found out that indeed these, and we metered the motors, and we indeed got what the theoretical fan curve showed us that we should. So we're playing around with the Vigilent system, trying to figure out how low to go. You reducing the speed of the fans. You want to save energy, but you want to give yourself enough margin that you don't create any hot spots and everything else. And what's great is that we've got all these wireless temperature sensors installed now. We can monitor exactly what's going on throughout the data center, checking to make sure that everything is okay, no hot spots are being created, and so far everything is going per plan. As I said, the original setup of the data center racks, they did a pretty good job of keeping the hot aisle cold aisle arrangement. And what it is what you really care about is the inlet to the IT equipment. Okay, and that's where we've got all this temperature sensors, because that's what you really care. The hot aisle can get as hot as it needs to get. It really doesn't affect the performance of the IT equipment. What you got to do is you got to keep the inlet nice and cool, but not too cool. As Nicole said, ASHRAE is saying that, we can raise the temperature, of the new equipment. You may still have some legacy hardware, IT equipment in the data center that, could probably get reliable operation at a slightly higher temperature, but maybe not as high as the brand new IT equipment that you buy, whether it's a server, a storage array, a switch. So what this does, this gives you the data that both the IT people and the facility people can look at and get some kind of comfort to say, okay, I'm reducing the temperature little by little. I'm reducing the speed of the fans slowly, making sure we don't get the hot spots. And you can even raise the temperature, the set temperature of the crack units, and make sure that you don't run into problems. But right now, you can easily identify where and when you have hot spots, and you can make changes to either perf panels or blanking panels, and make sure that you're getting the performance that you think you're going to get. So basically, it's data, and more data. Okay, that's what gives you the confidence, and that's what gives you the capability of keeping the data center reliably operating while saving energy. And the next slide is just one other thing that we've been doing some research on. It's a little more radical than this. Is we're actually operating data centers on 380 volts DC. And we're getting substantial amount of energy savings that way. And we've got demos around the world that we're doing that we're improving the power quality, decreasing the footprint, increasing the reliability, and reducing the energy consumption. So there's many things that you can do once you start taking a close look at what your data center is doing and getting the data in order to make a lot of these decisions. So that's my presentation, and I guess it's back to you, Dan.
Yep, thank you, Dennis. So now we've got about 10 minutes left, and we'll be taking questions. So if you have any questions, please submit them on the QA panel on the WebEx navigation pane. So we've got a couple questions already so far. And the first I want to direct toward Nicole. And the question is, I have a BMS system. Why can't my BMS system do airflow management like this?
Well, I think the easy answer is you don't have the temperature data that's critical for having that visibility of what's going on from a temperature and operational perspective within the data center. And also, I know there's a lot of fluid dynamic and computational fluid dynamics in the DCIM software that allows you to take that temperature data and then produce that visual map. So I don't think the BMS comes close to doing what these the Vigilent type systems can do.
Great. And Dennis, do you have anything you'd like to add?
Yeah, most BMS systems are pretty rudimentary. They'll tell you what the supply air temperature is, and maybe the return air temperature. But the thing that the computers care about is the temperature going into the IT equipment. So you need more data than the basic BMS system.
Great. And there's another question here, I think, kind of towards Nicole. It asks, when you were talking about consistent cooling, I think, Nicole, and the question says, how does the cooling management system manage the consistent cooling to get uniform rack temperatures?
Well, it's ongoingly monitoring the inlet temperatures, both at the bottom and tops of the rack, and adjusting the amount of, first of all, the supply temperature from the crack units, how quickly it's being blown into the room, so that it can keep adjusting based on the feedback of the temperature of the rack, if that makes sense.
Sure. Anything else to add, Dennis?
No, that's the answer. You care about the inlet temperature of the IT equipment.
Great. So one more. Let's start with you, Dennis. How would I know if my facility is at risk?
As we've been saying all along, you need data to know if your facility is at risk or not. If you don't measure anything, you don't know where you are. I mean, you can kind of get a little bit of a feel if you walk up and down, the aisles or around the equipment that you've got. If it's not, it's set up in a hot aisle, cold aisle. But you just need to know where you are. It's just like with PUE. If you don't know, what your IT equipment kilowatt load is, and your facilities, crack unit energy consumption is. You don't know what your power usage effectiveness is, and it's the same thing with the rest of DCIM. You need to know, what are the temperatures around, in front of all the racks. Data. I mean, you're making a bunch of guesses, which could really impact your reliability if you don't have instrumentation and data to analyze, how you're operating.
Great. Anything else to add, Nicole?
No, I think that's spot on.
Okay, another question here is, why can't I do this manually? Nicole, do you want to start?
Well, going back to that slide of the stressed out operator, is you'd have to have people running around taking temperatures ongoingly, and then somehow having the knowledge of knowing what to do with that temperature data. So I just don't think there's any way to do it manually.
Dennis, anything to add?
Well, you can do some of this manually, but you're taking more of a risk. You can actually put in a variable speed drive on these fan motors and reduce the speed. And you can kind of make a little bit of a judgment yourself, but without the proper data, up and down the racks, the rows of racks, you're putting yourself at risk. And you can do it manually, but it's obviously much better to let the system of wireless temperature sensors and the smart control of the fan speed, adjust as needed to make sure that you don't have any equipment that's in a hot spot that's going to cause any reliability problems and longevity problems too.
Great, and so we just have one more question here. I'm going to direct towards Dennis. How much monitoring and data do I need to be protected?
You need to have pretty good coverage of if you've got a lot of rows of racks. You need to have the midpoint maybe and the top of the rack measured every few meters in order to make sure that you don't miss some spot where you've got mixed flow and you've got hot air cycling back either through the racks or above the rack, causing the inlet of certain equipment to be overheated. So you don't need temperature sensors on every rack, but every 2 or 3 racks is probably an optimum kind of setting, and you need to measure build the thermal map in order to figure out okay, where am I possibly getting into trouble. And maybe what you can do is you can move perf panels around, again blanking panels or whatever, in order to adjust for that and still save energy and be reliable. So you don't need to measure everything, but you need a good amount of sensors around to figure out where you are. Great.
Anything else you'd like to add, Nicole?
No, I think that's a great summary.
Okay, we've actually got one more that just came in the last minute. The question is, I believe that many utilities provide incentives to reduce the cost. Is this correct? And I can comment on this one. Yes, it is correct, and many utilities, especially out in the Bay Area and on the East Coast, where there are a lot of data centers, are providing utilities to help reduce the cost of a cooling control system. Some small utilities don't have rebate programs in place, but typically the cost of a cooling control solution is financially attractive and can provide about a 2-year return on investment. But yes, the utility incentives certainly help. So that's all the time we have for questions today. If you have any more questions about cooling control system, please feel free to contact us and we can provide you some more detail about the benefits of a system like this. Thank you for attending.